Let's continue our investigation of areas in the plane. So as I mentioned on the very first day of class, one of the strategies in calculus is if you can't find something directly, then you approximate it and then figure out how to make that approximation better and better using some kind of limiting process. So I want to apply that in this situation. Let's say that our goal is to find the area in the plane of the region which is bounded above by the parabola, y equals x squared plus 2, bounded below by the x-axis, and it also lies between the vertical lines x equals 1 and x equals 3. So since we don't have a direct way of figuring out the area of this, this isn't a familiar geometric shape, let's see if we can approximate that area in some sense. What I'm going to do is break the interval between 1 and 3 into 4 equal pieces. So I'll split it in half at 2, and then split each of those intervals in half at 1.5 and at 2.5. Let me connect those points on the x-axis up to the curve y equals x squared plus 2. Notice that each one of these vertical strips has approximately the shape of a rectangle, and we know how to find the area of a rectangle. So let's see if we can approximate the area under the curve by actually squaring off the top of each of these strips so that it becomes an actual rectangle. Now to begin with, I'm going to choose rectangles which sit underneath the curve. So let's think of these rectangles as R1, R2, R3, and R4. If I calculate the area of each of these rectangles and I add the results together, then I'll get an approximation to what the area under the curve is, but the approximation is actually going to be a little bit low. It's going to be less than the actual area because of these gaps right here. So for that reason, the answer that we get, the approximation, is going to be called a lower sum because it's lower than the actual area. So here, where we're calculating lower sums, this particular lower sum is going to be the sum of the areas of rectangles 1 through 4. Let me make a chart, and then let's calculate the areas of those 4 rectangles. So for each of the rectangles, R1, R2, R3, and R4, the area of the rectangle is going to be base times height. So I'll take the height of each rectangle and multiply it by the base. And height multiplied by base is equal to area. I'll do that for each of the 4 rectangles, and then I'll find the sum. I'll add them all together. So I'm setting this up like an Excel spreadsheet. In fact, if you know some Excel, then after today's lesson, you'd easily be able to set up an Excel spreadsheet to find upper and lower sums like we're doing. So here we go. Let's look at rectangle 1 first. Notice that the height of the rectangle is this distance here, which is the distance between the x-axis and the curve at the left endpoint. So the height of the first rectangle is f of 1. When you plug 1 in, you get that y-coordinate. So the height of rectangle 1 is f of 1. And if I substitute 1 into this function, 1 squared plus 2 is 3. So the first rectangle has height 3. The base of the rectangle is the distance between 1 and 1.5, and 1.5 minus 1 is 0.5. So the base of the first rectangle is 0.5. And then to get the area, it's height times base. And 3 times 0.5 is 1.5. Now let's move over to rectangle 2. The height of rectangle 2 is the y-coordinate of this point, which I can find by substituting 1.5 into the function. So the height of rectangle 2 is f of 1.5. Now here we might need to use a calculator. But the function is x squared plus 2. So to find f of 1.5, that'll be 1.5 squared plus 2. If you put that in the calculator, you get 4.25. The base of rectangle 2 is the distance between 1.5 and 2 minus 1.5 is 0.5 again. And then the area is the height times the base. 4.25 times 0.5 is 2.125. Notice that rectangle 3, the height of the rectangle is given by the y-coordinate of this point, and that point's on the curve, so I can substitute 2 into the function and get the y-coordinate of this point. And 2 squared plus 2 is 6. At this point, I'd suggest that you pause the video and see if you can fill in the rest of the chart, and then come back and see what you get. If you have filled in the chart, then you should have found that the base of this rectangle was 0.5, and that the area was 6 times 0.5, or 3. And for the last rectangle, the height was f of 2.5, which is 8.25. The base, once again, was 0.5, and then the area was 4.125. So the total area of the 4 rectangles is the sum of these 4 numbers, which is 10.75. So what we know so far is that 10.75 is less than the actual area. Under the curve. So I know the area is approximately 10.75, and I know that it's actually something a little bit bigger than 10.75. So at this point, I don't know whether the actual area is going to be 10.8 or 12 or 15. I know that it's bigger than 10.75, but I don't yet have an upper bound. So what I'd like to do next is come back, and instead of using rectangles that lie underneath the curve to get a lower bound, I'm going to use rectangles that lie outside the curve to get an upper bound. So once again, I'm going to use 4 different rectangles, and I'm going to split them at 1.5, 2, and 2.5, and 3. But now for each of these strips, instead of using an inscribed rectangle, which lies underneath the curve, I'm going to use a circumscribed rectangle, which goes on the outside of the curve. Let's make another chart like this. And this time, let's calculate the areas of the 4 rectangles that are sitting outside the curve. I'll make the chart, and maybe do one example, and then I recommend that you pause the video and fill out the rest of the chart on your own. Okay, so for rectangle 1, the height of this rectangle I can find by where the rectangle touches the curve, and notice that that's at the right endpoint rather than at the left endpoint. So to get the height of this rectangle, I'll have to substitute 1.5 into the function. Fortunately, we already calculated that over here. F of 1.5 was 4.25. The base is still 0.5, So the area is going to be 2.125. So here's the point where I'd suggest that you pause the video, fill out the rest, and figure out what this upper sum is going to be. This is going to be an upper bound on what the area underneath the curve is. What you should find is that the first three rows match the last three rows over here. And for this last rectangle, the height's given by the value of the function at 3, which is 11. The width is 0.5, so that one has an area of 5.5, and the sum is equal to 14.75. So what we know now is the true area is somewhere between 10.75 and 14.75. Something like this could be called an interval estimate of the area, because we're saying that the area lies somewhere in the interval between 10.75 and 14.75. So, what I want to do next is see if we can improve this estimate. Remember, that's the calculus strategy. First of all, you come up with an estimate, and then you come up with a way of improving it. Well, an obvious way to improve this would be to use more than 4 rectangles. Now, ideally, if we wanted to get a great estimate, we would use 100 rectangles. But since we're still doing this by hand, we're just going to move from 4 rectangles to 5 rectangles and see whether this estimate gets better. And that we'll do in the next video.